course we're doing lecture. Look at this.
Do test.
Yeah. Don't just take a test on a test day. Yeah, I completely forgot about that, so not doing the test today. We'll do the test next class, I guess. Maybe. Let's count on it next time. I might just give you a test 3 and 4 together. Because chapter 3 and chapter 4 are so closely related.
Chapter 4 is...
What's chapter 4?
So we're starting chapter 4 today. Chapter 3 is derivatives. Chapter 4 is applications of derivatives. So the two are very closely related. That's why I made chapter 4 also, made us go until chapter 4 to do the midterm. Most calculus classes would do the midterm after what we've already covered. But I'm going to do it after chapter 4, so we're going to have a kind of a lopsided year where we do...
Oh, mid after.
Yes, so we kind of have a lopsided where we do more in the front and less in the back.
Which is awesome.
Anyways, starting on today's material, so now we're looking at applications of derivatives. We're not going to have a whole ton of new theory thrown at us. Just going to be using derivatives now. Okay, so quick definition, pretty straightforward definition. We have a notion of a function achieving an absolute minimum and an absolute maximum. What's the absolute minimum of a function? It's its lowest point.
Okay.
What's the absolute max?
Highest.
The highest point. Straightforward. And here's a precise definition. The function f has an absolute max or min, depending on which one you care about, at some point c in its domain, provided that, so when is it an absolute max? When is f of c an absolute max? When it's greater than or equal to every other point of the function. Then we call it an absolute max. When is it an absolute min? When is f of c an absolute min? When it's less than or equal to every point in the function. We call f of c, whether it's a max or a min, we call an extremum. It takes on an extreme value at that point.
Okay, that makes sense.
All right, quick sanity check. Let's look at the function f of x equals 2. Does that function have a max anywhere, an absolute max anywhere?
Yeah.
It's just a constant function 2. Does it have an absolute max anywhere?
2.
Yes.
2. Does it have an absolute min anywhere?
2.
2. So every single point we plug into the domain here gives us an absolute max.
Mm-hmm.
So every single point, it has an absolute max at every point, and it has an absolute min at every point. So there isn't one absolute max necessarily, and there isn't one absolute min necessarily.
Yeah.
Look at one more weird case. Let's just look at something like a sine function or a cosine function. Right? Absolute max, absolute min. Absolute max, absolute min. And it goes on its merry way. So not necessarily just one. Good so far?
Is that sine and cosine function?
Yeah, both sine and cosine. It's just one's just a shifted version of the other one.
Yeah.
So since I didn't draw your axis, it's whatever you want it to be. Pick your own axis. Okay. So doing a quick example. Let's look at this function y equals x squared, just a simple parabola, right?
Okay.
Now let's look at it on the domain of negative infinity to infinity.
Oh, yeah. Okay.
So going everywhere. Question, what's the absolute min of this function?
0.
0. It's the lowest point it reaches. What's the absolute max?
Lowest. What determines low? Because isn't a negative low?
Yeah, a negative would be lower.
Well, it goes on to the negative side.
What is the height of the function at 2? 4. Is 4 negative? It's the value of the function at the point. It's not c, it's f of c.
Okay.
So we don't care that this is negative 2. We don't care about negative 2. We care about f of negative 2. And what's f of negative 2? 4, which is much more than 0.
Okay, that makes sense.
Okay, so the absolute min is 0. What's the absolute max?
Infinite.
Infinite. Infinite is not a number.
As it approaches infinite.
What's the number?
The limit.
We're looking for a number.
There's no number.
There is no number, so it has no absolute max. It has an absolute min, it does not have an absolute max. So a function is not guaranteed to have either an absolute min or an absolute max.
So wouldn't that be infinity?
No, it doesn't have one.
How do you write that?
Infinity is not a number. It doesn't have an absolute max.
See, okay.
What's the biggest elephant in this room?
The one that's not in here.
There isn't one. What's the highest point this function reaches? There isn't one.
That makes
There is no highest point the function reaches. So it has a min at 0, and it has a max at nowhere. Now, let's look at this same function, but let's make its domain 0 to 2. So now we're saying our function starts right here and ends right here. So ignore the rest of that.
Okay.
Now, what is our absolute min?
0.
0. And what's our absolute max?
2.
2. So in that case, had an absolute min, had an absolute max.
Okay.
Let's make it slightly different. Let's go from 0 to 2, not including 0. So we have a hole right here. See if I can somehow get that to work. We have a hole right there, but we still include that point there. What's the absolute max? Still just 2. What's the absolute min?
0.
0. There is no point in this function that gives us 0. In order for 0 to be the absolute min, we would have to find a c in our domain such that f of c is less than or equal to all f of x. 0 is not in the domain, so I can't plug 0 into this function.
That's right.
So what is its min?
As it approaches 0.
So you gotta give me a number. None of this, well, whatever you think about hard enough.
Yeah, there is no number then.
There is no number, so it has no min.
Okay.
So has no max, or had a max, has no min. And then finally, if we looked at from 0 to 2, so we have a hole up here.
No min, no max.
It has no min and it has no max. So there's no reason that a function has to have a min, and there's no reason that it has to have a max. An absolute min and an absolute max. Good?
Yep.
So we've looked at a bunch of weird cases. No min, no max, infinitely many mins, infinitely many maxes. A max and a min and a max. Okay.
Okay.
So our first theorem here. If f is continuous on some closed and bounded interval ab, then f has an absolute max and an absolute min on that interval.
Meaning an actual number.
So I gave you some cases here where it did have a max and it didn't have a max. And it did have a min and it didn't have a min. What does this say? This is saying if f is continuous and its domain includes this closed interval a to b,
Okay.
then it's guaranteed to have a max and it's guaranteed to have a min.
Okay, yeah, that makes sense.
I should have written out the name of this theorem. It's a very common theorem. It's called the extreme value theorem. EVT.
Wait, is that it? Or are we still getting into it?
Huh?
Yeah, man, sorry.
Just a very famous theorem. It's called the extreme value theorem, a very useful one. Unfortunately, we don't get to prove this theorem in this class because it relies on the completeness axiom. We did prove this in topology, you might remember, and it was dependent upon the fact that the domain had to be compact. And in the standard topology on R, a compact set is one that is closed and bounded. So that is a compact set, so it's a consequence of compactness. So we don't get to prove it in this class because we're not using all our axioms rigorously, unfortunately. It's just like we already did the intermediate value theorem. We remember that one? IVT? Intermediate value theorem. That was if a function is continuous and it takes on 2 points, then it takes on every value between those 2 points.
Okay, yeah.
That's the intermediate value theorem. The extreme value theorem is if it's continuous on some closed bounded interval, then it has a min and it has a max, and then the last one we'll do is called the mean value theorem, MVT. And those are 3 very useful, very common theorems that we use a lot. So unfortunately you don't get to prove it. Let's make more explicit what this says. What are we saying? So if f is continuous on the closed interval AB, then f has an absolute max and min in that interval. Or in other words, what we're saying is there exist 2 points in the domain. There exists x1 and x2 in our closed bounded interval, such that f of x1 we'll call it little m, f of x2 we'll call it big M, and little m is our absolute min, and big M is our absolute max.
Okay.
Make sense?
Yeah, that makes sense.
Okay, so quick examples. Here's a bunch of different functions that I have drawn up. Notice that all these functions are continuous. What's our simple-minded version of continuous for this class?
No holes.
Yeah, you can draw it without picking up your pencil.
Oh, yeah,
That's the simple notion. We know the exact notion of continuity.
Yeah.
What does it mean for a function to be continuous at a point?
It's not broken at any part.
Well, what's the exact definition?
Oh.
Your textbook does not say a function is continuous at a point if it's not broken at any part.
It says-
For any x1, we can find a delta.
Oh, that makes sense.
You're thinking of how we define the limit of a function at a point. But for a function to be continuous at a point, it just means that the limit of the function at the point is equal to the value of the function at the point.
Oh yeah, we did.
Right? It just means that the limit as x approaches c of f of x is equal to f of c. That's all it's meant to be continuous. But our simple-minded notion is just, can you draw it without picking up your pencil? And so all those functions, there we have a bunch of continuous functions defined on some closed bounded interval a to b. And notice that no matter how I try to draw it, however I scribble, as long as I do a continuous function, I have no choice but to put a max in there somewhere and to put a min in there somewhere. I guess one more example that would have been nice to draw, we kind of already talked about it, but the one kind of case I don't really have drawn out there is a continuous function. So something that looks like this. A, B. Okay, and now we kind of have every case.
A linear function.
Right. Well, it is linear since it's a line, but it's also just a constant function.
Yeah.
So here's some function where it achieves a max and a min somewhere between the endpoints. Here, it achieves a max somewhere between, but we have to rely on one of the endpoints to be the min.
Yeah.
So here, max and min somewhere in between. Here, the min was at an endpoint, but the max was somewhere in between.
Okay.
Here, both the endpoints were the max and the min. Here's the
Oh,
max,
yeah, that's
here's the
good.
min.
Okay.
And then here, one of the endpoints was a max, and the min was somewhere in between. We are going to be very interested in finding where our functions have these little bumps in them. Top bumps or bottom bumps. This is something we are extremely interested in for all sorts of applications. In fact, this is what your AIs are essentially doing. They are looking at some hyperdimensional plane, but just think about it as a plane with a bunch of bumps on it.
Okay.
And what they are doing, what back propagation is doing, is it is finding the top of some hill in the surface. That's ultimately what training an AI is.
What does that mean?
So if we were to draw out a piece of the hyperdimensional plane, it's really like you have to think about it as like a 50-dimensional plane or a 1,000-dimensional plane or whatever. We can't picture that. But some plane, so the surface of the plane would look something like this. And in general, the height is telling us how good our AI is at answering the questions. And so if we can get our AI here, then it's doing much better at answering the questions than if it's right here.
How do they measure that?
Well, we can't get into it quite yet, but you know when your AI answered the question right or wrong. I say, AI, is this letter an A? And it's going to say yes or I say, what letter is it?
Oh, so test.
Right, so you actually test it, you actually train it, and you know yes or no, and you can score it. And based off of how good or bad the score is, you can tell it go up a little bit higher. The algorithm helps it find the top of one of these hills and settle in on the hill. And the function set up that the higher you are up, the better it is at answering the questions.
Strange.
So finding local mins, local maxes, this is something we are very interested in. If we're interested in physics, we're interested in AIs, we're interested in economics. It's a very useful thing. So we're going to spend a lot of time talking about how we find these maxes and mins.
Can you just use looks and intuition?
Can't you just use what?
Intuition and just looking at it.
No, because I can't look at the solution space for an AI. I have no clue what that looks like, and there isn't some picture we can draw of it. If I could just draw out the picture of the solution space of the AI, then yeah, I could say, oh, AI, choose this point. Instead, it's like it's blindly looking around as though I go and I stick you on some surface somewhere. You're completely blindfolded. You're in a desert somewhere, and I say, find the highest hill you can. And that's kind of what the AI is doing. It's kind of feeling around, seeing which way makes it go up some, and trying to find that local hill. And we'll figure out how to do that in the one-dimensional case. It's called Newton's method, and that will be in like 2 sections, 3 sections.
Okay.
But same idea. So, very interested in this. We're going to be doing a lot of finding these tops of bumps, bottoms of bumps. Okay, so now we have the notion of a local min and a local max. Absolute min and absolute max are the highest points on the function and the lowest points on the function. A local min and a local max are highest points if you kind of look at just a piece of the function.
Okay.
So if I had a function like this, then we have a local min, because that's the smallest piece of the function when we look right here.
Yeah.
We have a local max, local min, local max, local min,
Oh.
local max, local min, local max, local min.
How do you determine that? Like when to break it?
Well, it doesn't matter. Just imagine if there's any open interval I can place around it, doesn't matter how small. If there is one I can place around it where it is a max on that interval, then we're good.
Wouldn't that be everything?
No. So you might think, wouldn't this be one if we place a small enough open interval around there?
Oh no.
Because we're using an open interval, say that this is a point A. So let's look at the open interval. So we're saying that this is A, right?
Okay.
Draw my x-axis really quick here. So this is a point A. Then an open interval around it would be a teeny bit to the left of A and a teeny bit to the right of A, right?
Mm-hmm.
Now look at the function on that interval.
Oh, I see.
It has a hole here, it goes up, and it has a hole here. So what is the min on that interval?
It's not.
It doesn't have one, just like what we had over here. Those little holes make so that it doesn't have.
Yeah.
So you take as small as open interval as you want, and take it all across your function. And anywhere where on that teeny interval, if you find a max, then that's a local max. On that teeny interval, if you find a min, it's a local min.
Okay. That's
Now, an absolute max will always also be a local max, and an absolute min will also always be a local min.
yeah, because it's base.
Okay. So, exact definition now of this. F has a local max or min at some point C, provided that f of x is less than or equal to f of c, or f of x is greater than or equal to f of c, depending on if we're talking about a max or a min, for all x in some open interval containing c. Pick any small open interval you want containing c.
Yeah.
If c makes that point a max on that interval, it's a local max. If c makes that point a minimum on that interval, it's a local min. Okay, so let's look at this function. Starting at the point A. What do we know about this point A?
So local min.
It's a local min and
It's continuous.
an absolute min.
Yeah.
So this is both a local and an absolute min. What about this point?
Local max.
Only a local max. What about C?
Local min.
Only a local min. What about D?
Absolute max.
Absolute max. What about E?
Wouldn't it also be local max too?
Yes, absolute max. Every absolute is also a local. Perfect.
Oh, yeah, you said that.
And then
And then that's local.
local min or max?
Min.
Okay, good.
Yeah, it's pretty straightforward.
Now, wanted to make special note of this point for a second. What is the derivative at that point?
Local min. Or the absolute.
What's the derivative of that at that point? What's the slope at that point?
You would have to draw a tangent line.
Okay, I'll draw a tangent line. Here we go. I'll draw another one. Here we go. I'll draw another one. Here we go.
Pretty sure it's supposed to be 0.
It's undefined. Remember? When you have corners, the derivative is undefined. There's no slope there. The common example we use over and over again is the bottom of the absolute value function. And we prove that the bottom of the absolute value function has no slope. You look at the limit as we approach from the left, what's the slope? What's the slope of this line? -1. If we approach from the right, what's the derivative? +1. That's a positive slope.
Yeah. Okay.
So we get a negative slope from the left, a positive slope from the right. So what's the slope right there?
Oh, it's a corner.
It's a corner. It doesn't have a slope right there. It's undefined. Because the limit as you approach from the left is -1. The limit as you approach from the right is 1. A function doesn't have a limit at a point if approaching from the left you get one value and approaching from the right you get another value. It's the exact same as when a function jumps at a point.
Okay,
Remember, a derivative is a limit of a slope. So the limit of the slope over here, -1, the limit of the slope over here, 1. So what's the slope right at the corner? Doesn't have them. Corners don't have slopes. Okay, so notice, I told you that we're going to be very interested in these points.
The spikes?
Yes, these tops and bottoms.
Okay.
These mins and maxes. And so notice the derivative at all these points. First off, it could be the point that we have a min or a max at our endpoint, right?
To take a derivative?
We can't talk about the derivative at that point.
Because there's no left hand.
We can only talk about the right-hand derivative at that point and the left-hand derivative at this point. But the point is, notice that all the points that we care about, they're either endpoints, we care about those two. Thank you.
Are you missing him?
Yes, we are missing Caleb. And then the Audrey's just working on a senior project here. Okay. We're over here. So notice that all the points of interest, what's going on? Either they were endpoints, right?
Yeah.
Or, what's the slope here?
It's not
What's the slope at the top of a hill?
It's
At the very top?
0. Or
0.
Okay.
If I placed a ball perfectly on the top of the hill, which way would it fall?
Nowhere. Okay.
Nowhere, because the slope is 0. Or draw the tangent line. Slope is 0. At the bottom of the hill, what's the slope?
0.
0. Or at a point like this, what's the slope?
It's broken.
It's broken, it's undefined. And so notice that the points that we care about, because we're going to be looking for these maxes and mins all the time. So at these maxes and mins, notice what happens. Either they're endpoints, or the derivative is 0, or the derivative is undefined. And it's going to be one of those three cases. So this is one of the ways we can start finding these points. You don't have to draw out the picture and rely on the picture somehow to figure out where the point is.
Yeah.
That would be a pain. Imagine that your function had a 0 clear down at the x-axis 20 million. You don't want to have to draw the picture that long to finally find that point.
Yeah.
We want a way to be able to calculate these points. So, these points, there's three things that we check for when we try and find these points. One, we always check the endpoints. They could be a max or a min.
Aren't they always?
They're always a local max or a local min.
Oh, yeah, that's right.
Now, the question is are they an absolute max or an absolute min?
Yeah.
And that's something else that we'd be interested in. So your absolute max and your absolute min, they can either be your endpoints, or they're going to be points where the derivative is 0, or the derivative is undefined. And it's always going to be one of those three cases.
Yeah.
Okay, so we're going to do a lot of find the absolute max and min of some function.
Okay.
And we check those three things. Okay, next theorem. If f has a local max at some point c, and the derivative at c exists, then the derivative is 0.
Oh, yeah, because you can't take a derivative going backwards.
Well, up here I just explained to you that a max will only show up at,
Zeros.
The derivative.
sorry, this is c, I did not write that very good, in the interior. So we're not including the endpoints. So if f has a local max at c in the interior of the function, so ignoring the endpoints,
Oh, yeah, because you can't do that.
then we're going to prove that if there's a derivative at that point, then the derivative is going to be equal to 0.
Okay, that makes
I told you intuitively that that's going to happen, and tried to make it appeal to your intuition. Now I'm going to prove that that will in fact always happen. You with me?
Yeah.
Okay. So let's get started. So assume that f of c is a local max on some interval a to b, some open interval a to b. Why the open interval a to b? Because we're not going to include the endpoints. So we want c to come from an open interval. It's going to be in the interior. We're not talking about endpoints.
Okay.
You with me so far? Okay. So assume f of c is a local max on some open interval a to b. What does it mean for f of c to be a local max on some open interval? It means that f of c is greater than or equal to f of x for all x in that open interval. Pick any x in that open interval, it's going to be less than or equal to f of c.
That makes sense.
Because f of c is our local max on that interval. Good so far?
Yeah.
Okay. Now, what is the derivative of f of c equal to?
Yeah.
It's equal to the limit as x approaches c of f of x minus f of c over x minus c, right? Now, if our function has a derivative at a point, then its derivative approaching from the left and its derivative approaching from the right have to be the same thing.
Can you understand it again?
If I have a derivative at a point,
Okay.
that would be this limit.
Mm-hmm.
That would be the limit as x approaches c of f of x minus, that would be the derivative, right?
Yeah.
If the derivative exists at a point, if a limit exists at a point,
No.
then the limit approaching from the left has to be the same thing as the limit approaching from the right.
Okay.
So the way that you've seen this before is the limit as x approaches c of f of x, if that is equal to some number L, then we are guaranteed that the limit as x approaches c from the left of f of x is also equal to L, and we're guaranteed that if it approaches from the right, it's also equal to L. And that it's actually, that is the case if and only if this is the case, plus or minus, approaching from the right or the left.
Okay, that makes sense.
Okay? So if I know that the derivative, a derivative is just a type of limit, right? So if I know that the derivative exists at a point, then I know that the limit as x approaches c from the left of f of x minus f of c has to be the same thing as the limit as x approaches c from the right of f of x minus f of c over x minus c.
That makes sense.
These two limits have to spit out the same value. You with me?
Mm-hmm.
Okay. Now, let's notice what we can about this limit. What do we know about this limit? First off, keep in mind, what do I know about f of c?
It's local max.
It's a local max. So how does f of c compare to f of x?
It will be
F of x
bigger or equal to.
F of c will always be greater than or equal to f of x. Right? So f of x minus f of c will be negative or 0.
Okay.
You with me?
Yeah.
So the numerator here, just looking at the numerator will either be negative or it will be 0. Good so far? Now we're taking the limit as x approaches c from the left. So is x smaller than c or bigger than c?
It's approaching.
If we're approaching c from the left,
Small.
It's smaller.
then x is smaller than c. So x minus c is
Negative.
negative. X is to the
Oh,
left of c.
Yeah.
So x minus c is negative. And so a negative over a negative is positive, or 0 over a negative is
0.
0. So this whole expression is either a positive number or 0. You see that?
Yeah.
So I'm going to write that this limit is greater than or equal to 0. Good?
Okay.
Okay. Now for the next one, same type of analysis. F of x minus f of c. I know f of c is a local max. So once again, I know the numerator here is either negative or greater than 0.
Yeah.
Same logic as before.
Except we were approaching from the right. So now
But yeah, for the denominator, this time we're approaching from the right. So what's bigger, x or c?
X.
X. So x minus c is going to be
It's going to be
a positive number. And a negative divided by a positive is
positive or negative.
negative. And 0 divided by a positive is
0.
0. So this whole thing is less than or equal to 0. Right? Because it's either negative or it's 0. Okay. So I know that the limit as we approach from the left is greater than or equal to 0. And I know the limit as we approach from the right is less than or equal to 0. But this has to equal this. So what does my limit have to be?
0.
0.
Oh, that's pretty.
Let me give you pictorially what we just said. What did I say here? I said, as we approach, I said our derivative, as we approach a local max from the left is negative. Notice, the slope over here, oh no, this is positive. As we're approaching from the left, the slope is positive.
Oh, yeah.
So look over here, as we're coming up the hill, our slope is positive.
Mm-hmm.
All the way up until we get to the point 0. That's what this expression is saying.
Yeah.
If we approach our max point from the left, our slope will be positive or equal to 0 the whole time. This bottom one says, if we approach our slope from the right, our slope will be, or if we approach our max from the right, our slope will be negative or 0 the whole time. So, hopefully now that is pretty intuitive, and hopefully you also understand the math.
Mm-hmm.
Make both those connections. Okay, so if the limit is greater than or equal to 0 and the limit is less than or equal to 0, the limit has to be 0.
Yeah, that makes sense.
Or sorry, the derivative. The derivative is greater than or equal to 0, the derivative is less than or equal to 0, then the derivative has to be 0. And so I proved that the derivative is 0 at a local max. Proving it for a local min is almost identical. You just swap all your inequality signs, and it's the same thing.
Okay, that makes sense.
Okay, so we won't bother with that. All right, our next definition. An interior point, see in the domain of our function d, whatever the domain of the function is called a critical point, provided that the derivative at that point is 0 or it's undefined. We just call it a critical point.
Okay.
If the derivative is 0 or undefined, we call it a critical point for some interior point. So in other words, B here, critical point. C, critical point. D, critical point. They were points where the derivative was 0 or undefined in the interior.
Oh, or undefined. Okay.
So we don't include A and E because those are endpoints. We're only looking at interior points.
It's basically either a local max or a local min, excluding your.
Our local maxes and local mins will happen at critical points, but if a point is a critical point, does it have to be a local max or a local min?
Yes.
Yes. Let's see. First off, imagine a function like this, the cubic, x cubed. Let's look at y equals x cubed.
Okay.
So that function roughly looks like this. Can't draw it very well. Where here's our xy axis, right? What's the derivative at 0? 0. But at that point is neither a local max nor a local min. But it is an inflection point.
What?
Sorry, a critical point. Right? Because what's the derivative there? What's the derivative of 0? Let's really quick calculate y prime. What's y prime equal to?
It's 3x squared.
3x squared. So what is the derivative at 0? 0. So the derivative is 0, but it's not a local min or a local max. So the point is, if it's a local min or a local max, it will be at a critical point. But just because you have a critical point does not necessarily mean it's a local min or a local max.
Okay.
That make sense?
Yeah.
Because there's also one more way that we could get a weird function, and that is looking at this one's inverse function. If we look at y equals the cubed root of x, then that function, it's like this function but tipped on its side. So it looks like this. And once again, the slope at 0 now is going to be undefined because it's going to be straight up and down. However, that function, that point is neither a min nor a max. So the derivative can be undefined, and we still don't have a min and a max. And the derivative can be 0, and we still don't have a min or a max. But if we have a min or a max, then the derivative is for sure 0 or undefined. Unless, of course, it's an endpoint, but for an interior point.
Yeah, that makes sense.
Good. Okay. So with that, let's do some examples. All right, so we're going to find the absolute min and max of a bunch of these functions on their different domains. So starting with this one. X squared on the interval -2 to 1. You with me?
Yeah.
So we're finding an absolute min or an absolute max. We are guaranteed that the absolute min and absolute max occurs either at your endpoints, where the derivative is 0, or where the derivative is undefined. You with me? So really quick, let's test our endpoints. So we start by looking at what is f of -2 equal to? 4.
Wait, what was the question?
we're testing our endpoints. So I'm finding the value of the function at the endpoints.
Okay. So.
What's f of 1?
1.
1. Okay. Now let's look at the derivative of this function. What is f prime of x equal to?
2x. Yeah,
2x. So where is it equal to 0? Where is the derivative 0?
0.
0. So what is the value of our function at 0?
0.
0. Where is our derivative undefined? Nowhere. So we don't have any other points to check. So we are guaranteed that our absolute max and our absolute min occurs at one of these 3 points. The lowest of those points now is guaranteed to be your absolute min. The highest of those points is guaranteed to be your absolute max. So on this interval, -2 to 1, the lowest point of the function will be 0, and the highest point of the function will be 4.
What if you were dealing with like -60 to 60? Then it's a lot harder to find it, isn't it?
No. We won't go 60 to 60, but let's just go minus
Something huge.
10 to 10.
Okay.
You with me? So we check those 2 points. What is f of minus 10? 100. What is f of 10? 100. Where is the derivative 0? At 0. So those are the 3 points. We're guaranteed one of them has to be an absolute min, and we're guaranteed one of them has to be an absolute max. In this case, we have 2 absolute maxes, because it's a parabola. It's the same height at -10 as it is at 10.
How did you know to put in 0? Why are you putting in 0?
Where is the derivative equal to 0? So here's our derivative, 2x, right?
Yeah.
Okay, so now we're asking, where is 2x equal to 0? What value of x makes 2x equal to 0?
Only to 0.
Yeah,
But if it was another number, then we would use the other number.
here's our derivative function, right?
Yeah.
We know that our max occurs where the derivative is 0. Or our mins occur where the derivative is 0.
Yeah.
Where is 2x, our derivative, equal to 0?
0.
At 0. So that's why we tested the point 0.
Okay.
Good?
Yeah.
Alright, let's try another one. So that was a pretty obvious one because it's just a simple parabola and we could have guessed just from looking at it. Here's one that's not so simple. 8t minus t to the 4. And we're going to look at on the interval of -2 to 1. I have no clue where this thing takes on a max or a min. Now you can't just look at it and see it.
That was, yeah, okay.
Yeah, before it was just a parabola, and obviously the lowest point is 0, and the highest point is whichever one of those goes further in the x or y direction.
0 is still an option for that.
Yeah, 0 is still an option to this, but the question is, well, let's just work through the problem. So here's our problem. We're looking for the max and the min, right?
Mm-hmm.
So first off, we have to check our endpoints, where the derivative is 0, where the derivative is undefined. So let's check our endpoints. What is g of, what's our first endpoint? -2. When I plug -2 into that, what do I get?
2 times 4.
-2 times 8 is -16. And -2 to the 4 is 16, right?
So 0.
It's -32 because you minus.
We're subtracting, right? So negative minus positive is more negative, so -32. Good?
Yeah.
Now let's check g at our other endpoint 1. And what do we get?
7.
Just 7. Okay, now let's see where our derivative is 0. So first off, let's calculate our derivative. So what is g prime of t equal to?
8 minus 4t to 30.
And the question is, where is that equal to 0? So I want to know where 8 minus 4t cubed is equal to 0. What t makes that true?
You would have to guess a whole bunch of times.
No, we don't have to do any guessing. Move the 4t cubed to the other side and we get 8 is equal to 4t
Oh,
cubed.
yeah, you can't do that.
Divide both sides by 4. Yeah, I'd rather solve for it than guess for it. Equals t cubed. And so finally, t is equal to the cube root of 2.
Oh, what the heck?
So that is the value of t that makes our derivative 0. Right?
Yep.
And that's the only one that makes our derivative 0. So now we need to check that point. What is g at the cubed root of 2 equal to?
G's,
8 times the cube root.
no,
We're going to need to give ourselves some verticals or some horizontal space, so I'll write down here. So we're looking for g at the cubed root of 2.
Yeah.
What is that equal to? Well, that's going to be 8 cubed roots of 2
and then 4 cubed roots of 2.
minus how many cubed roots of 2?
4 into the power 4, so
Wouldn't that just be 2?
2 cubed roots of 2.
whoa, why?
So let's write that out. So we basically have 2 to the 4/3. You with me? The cubed root of 2 is the same thing as 2 to the 1/3. And we're raising it to the 4th power.
Okay, I didn't know that.
Let me write it out in just a couple steps. So here's what you were comfortable with. We're doing the cubed root of 2 to the power of 4. Just evaluating this term.
Yeah.
Okay. Cubed root is the same thing as 2 to the 1/3.
Okay.
When you have exponents to exponents, that's the same thing as multiplying. 2 to the 4/3.
I'm gonna be 12. Oh, it's 1/3. Okay.
Good so far?
Yeah.
And now, that's the same thing as 2 to the 1 times 2 to the 1/3. When you multiply terms, you add exponents. What's 1 plus 1/3? 4/3.
Oh, okay, I see.
That's one way to think about it. Here's another way you could have thought about it. Writing the cubed root of 2 to the power of 4, you can do your power first and then take your cubed root. So this is the same thing as the cubed root of 2 to the 4. And now we have to pay 3 to pull a 2 out. And so we can do 2 times the cubed root of, now we only have 1 left. Because I had to pay 3 to pull a 2 out.
Okay. Yeah, that makes sense.
Good? Okay. So, that in other words comes out to 8 cubed roots of 2 minus 2 cubed roots of 2 is
6 cube roots of 2.
6 cubed roots of 2. Okay. So, I am guaranteed, let's box it, maybe use a different color so that you can see the points we calculated. We calculated this one, and this one. I'll just box this. So we're guaranteed one of those is our absolute min, and one of those is our absolute max. So where's our absolute min?
7, -32.
One.
-32. This is our absolute min. And what is our absolute max?
The bottom one.
Is it 7 or is it 6 cubed roots of 2?
6 cube roots of
Not completely obvious just from looking at it, but yes, this one happens to be it. You calculate that, I think it comes out to around 7.4.
It has to come out to more than 1.
Right, but more than 1 times 6 is not necessarily enough to get you past 7. So, don't be too quick to assume, in this case,
It's true.
it's true. Okay. So now, our next example. Doing this example. Should have enough space just here. Okay, so here's our function. Raising something to the 2/3 power. So first we gotta check our endpoints. So what is f of -2 equal to?
-2.
You can either square it, then take the cubed root, or take the cubed root, then square it. I'm gonna square it, then take the cubed root.
So 4 and then.
So I'm gonna write it as a cubed root of 4.
Okay.
And that's probably good enough for our purposes. Okay, what is f at 3 equal to?
9.
I'm going to square it, then take the cubed root, and so I'm just going to write it as a cubed root of 9.
Cube root of 9.
Because we don't really need to calculate this, I just need to be able to compare this number with that number, and see which one's bigger or smaller. And that's all we really care about. Now, what's our derivative? What is f prime of x equal to?
It's 2/3 times x minus 1/3.
To the minus 1/3, which is the same thing as, I'm going to make my exponent positive by bringing it downstairs.
Cube root.
So I'm going to write this 2 over 3 cubed roots of x. You okay with that?
Why is 2 over x?
2's in the numerator. 3's in the denominator. If I'm going to put that down in the denominator, I have to make its exponents positive.
Okay.
Writing it this way is identical to if I had written it this way.
Oh, that makes sense.
If I have 1/2 4 times, that is the same thing as just 4 halves, or in other words, 2. So multiplying by a term is the same thing as multiplying the numerator by that term.
Okay. That's interesting. Okay.
Alright, so here's our derivative. Where is our derivative equal to 0?
0, not 0.
What value of x makes this whole term 0?
That's nothing.
Nothing! Right? The only way you can make a fraction go to 0 is if you can make its numerator go to 0.
Which you can't.
Which you can't. Now, where is the derivative undefined?
0.
0. So we still need to check the point 0 because that's where our derivative was undefined. Remember, we got to check points where the derivative is undefined or 0.
Mm-hmm.
So in this case, we still need to check f of 0. So what is f of 0 equal to?
Undefined.
No.
Oh. What do you? Where
Can you have f of 0 because it's in the interval negative?
What's 0 times 0?
0.
Now take its cube root. What times what gives you 0?
0.
What number such that when you multiply it by itself 3 times gives you 0?
0.
0. So that was really easy to do.
That's what I thought you said 0.
What is a cube root? Let's remind ourselves of cube root for a second. What's the cube root of 8? What am I asking for?
2.
It's 2, because 2 is a magic number such that when I multiply it by itself 3 times, I get 8. What's the cube root of 0? What's a magic number such that if I multiply it by itself 3 times, I get 0?
0.
0. So raising 0 to powers, super easy to do. And taking 0 and finding nth powers of it, or nth roots of 0, real easy to do. Always 0. Really nice number. Okay, so now we're guaranteed that one of these is our local max and one of these is our local min. At least one of them. Remember, they could have the same value.
Yeah.
So what is our local min, or our absolute min, sorry, absolute, 0. And what's our absolute max?
9. The
Cube root of 9. Perfect. Good?
Yep.
Not too bad? Okay, so there's some examples. You'll do a lot of that.
Yeah.
Okay, now we're going to move on to a famous theorem called Rolle's theorem. Starting our next section. So that was ending one section. The first section was all about the extreme value theorem, which is this theorem right here, and finding extreme values, mins and maxes. Now we're moving on to the mean value theorem, is what the next section is all about. What is the mean value theorem intuitively? Let's say that Jana here goes to Salt Lake City. We'll say that it's exactly 300 miles away, and we'll say it takes him 5 hours to do it.
Okay.
What was his average speed?
Distance over time.
Yeah, so you went 300 miles,
Over.
and you did it in 5 hours.
So 60.
And it comes out 60 miles per hour. What does the mean value theorem say? It says, since this was your mean displacement, your mean velocity, your average velocity, we are guaranteed that somewhere along the way in that trip, you were going exactly 60 miles per hour.
No.
If 60 miles per hour was your average speed, then I am guaranteed at some point in your drive, you were going exactly 60 miles per hour.
If the function is continuous, then
Right, if our function is continuous.
Oh, okay. I shouldn't say.
But we're thinking about him driving along. Driving is a continuous operation, right? You can't be driving 10 miles per hour and then suddenly 20 miles per hour. You have to speed up or slow down to everything that you go to. Now, this makes intuitive sense because either you drove to Salt Lake the entire time going exactly 60 miles per hour, or there were times where you went a little bit under 60 miles per hour, which means that at other times you had to be going a little bit over 60 miles per hour. And the only way to get from under 60 miles per hour to over 60 miles per hour is to cross 60 miles per hour. So you can see how the intermediate value theorem would play a part in proving this.
Okay.
So that's what the mean value theorem says. Pictorially, what it says is that if I have some function, So think about this as your position function. You driving to Salt Lake, right? You might be going along, slow down, speed up, slow down, whatever. So this is 0, this is 300, we're doing it in miles. And then the slope here would be your speed.
Yeah.
So your average speed is the slope of this line.
And you're saying it's 60?
Yes, height is how far you went. This is 300. And then down here we have time. This is 5 hours.
Okay,
So
that helps.
how far you went each hour, right? So now, the green line here, the slope of the green line gives you your average speed. Your end point minus your start point, 300 minus 0, divided by your end x, divided by your start x, 5 minus 0, or 300 over 5, 6 speed. Right? It's the slope of this green line. The slope of this green line, it went up 300 when it went over 5. So the slope is 60. And so now what the mean value theorem says is that if that was your average slope, then we are guaranteed that there is a point somewhere in between where the derivative at that point, the slope at that point, is exactly 60. Now there could be several of those points, but the point is we're guaranteed that there's at least one point where that's the case. And so if this were your trajectory, you'll notice that you were going 60 miles per hour there. Here you were going over 60, here you were going less than 60, over 60, less than 60.
You're saying when it's a flat line then it's at 60?
No, I'm saying when the tangent has the same slope as the green line,
Oh,
then it's 60.
Yeah.
So the tangent here, the slope here, and the slope here are all 60. So you're driving along, you're going slow, speeding up, speeding up, speeding up, speeding up, speeding up. Here you're going 60 miles per hour. Then you kind of start slowing down to 60 miles. Let's think. Oh, you got 60 here. Speeding up, got to 60, you're going over 60, then you start slowing down, back down to 60.
Okay, you speed up right at the end there before you hit 60.
We might be drawing something a little bit weird here. Either way, so we won't think too much about my stupid drawing. But the point is, there could be several times along the journey where you reach 60 miles per hour. But we're guaranteed that there's at least one point along the journey where you reach 60 miles per hour. Because you could have also just taken off going super fast and then went like that, and so 60, you would have only achieved it somewhere right here. Or you could start out the journey super slow and then shot up like that, and then your 60 would have been just one point somewhere along right here. Or you could have just gone 60 the whole time. But no matter how you do it, no matter how you draw a line from here to here, the tangent somewhere at that line is going to be exactly the slope of this line at least one point. You with me?
Very small point.
Okay, so we're going to start out by proving a special case of this called Rolle's theorem. Rolle's theorem is going to be that if I got some function on some closed interval a to b, and the function has the same height at those 2 points, then if my function is continuous in between, no matter how I draw this, I will have to make the slope 0 somewhere.
Correct.
So it's a special case, because what's the slope of our green line now from this point to this point? A and B if they're the same height. So if I just draw the line that connects them, the slope's 0. So it's just a special case of the intermediate value theorem. We're first going to prove a special case of the intermediate value theorem, then prove it in general. So what that means now is no matter how I connect this to this, somewhere along the way, my slope is going to be 0.
Is it?
There's no way for me to draw from here to here without somehow making my slope 0.
If it's a lightning bolt all the way down.
So, what am I doing?
Draw a lightning bolt, like back and forth.
So I go down.
Rigid up, like a mountain chain.
Oh, so now it's not differentiable. So you can't have corners. Sorry, I said continuous the whole time, I meant differentiable the whole time.
Okay.
Good point.
Okay.
Okay, good. So if it's differentiable, in other words, no corners, then no matter how I draw it, I'll have to introduce a slope of 0 somewhere.
Okay.
That's Rolle's theorem. That's what we're about to prove. Thanks. Okay, so let's get started. If f of x is continuous on the closed interval ab and differentiable, DIFF or differentiable, I'll use cont for continuous and diff for differentiable over and over again. And differentiable on the open interval, a to b, so it has a slope everywhere in between the points a and b, maybe not the endpoints, but who cares, anywhere in between. Then there must exist some point c on the open interval, so not including the endpoints, such that the derivative is 0 there. Good. Okay. Now first off, since f is continuous, then f must achieve a max and a min somewhere on our closed interval a to b. How do I know that? Because of our very first theorem here.
EVT.
Because of the extreme value theorem. Good. From EVT. Okay. Then f must achieve a max min at some interior point c, where the derivative is 0 or undefined, or at an endpoint, one of the endpoints a and b. So the extreme value theorem tells us that it achieves a max and a min somewhere on the closed interval, and one of two things has to be the case. It can be a middle point, where the derivative is 0 or undefined, or it can be one of the endpoints. That's where your max and min have to be.
Yeah.
That's what we proved here.
Oh, yeah, that's right.
Is that if the max or min is a midpoint, and the derivative is defined, then the derivative is going to be 0. Right? Or it could be one of your endpoints.
Yeah.
Now I said that our function is differentiable, so that means the derivative is never undefined.
Yeah.
So all we care about is it either has to be where the derivative is 0 or an endpoint. If my derivative is defined everywhere, so I'm guaranteed not to have any corners, then my max or my min has to be either at the endpoints or somewhere where my derivative is 0. That's what we said here. If it's a local max or min and the derivative is 0, and the derivative exists, then it must be 0.
Okay.
So if my max or my min, they can either be the endpoints or a point in between. If they're a point in between, the derivative has to be 0 there. We can't have undefined because my function is differentiable. No corners. Okay, so we got to handle those two cases. I got to handle the cases where it's a middle point or where the max and the min are at an endpoint. So if either the max or the min are at an interior point C, then I instantly know that the derivative at C is
0.
0.
The derivative.
Right? What are we looking for? I'm looking for a point C where the derivative is 0. That's what we said with Rolle's theorem. Rolle's theorem, I'm saying no matter how I draw this, I can always find some point C in here, such that the derivative at C is 0. That's what I'm trying to prove. Okay, so if our max or our min happens at an interior point, the derivative is going to be 0 there.
Yep.
Okay, so if either the max or min are at an interior point C, then the derivative at C is equal to 0.
Okay.
We know it's not undefined because our function is differentiable.
Yeah.
So then there's our C. Okay, so now let's handle the case where our max and min are not the interior points. If our max and our min are not the interior points, where are they?
Endpoints.
There are endpoints. So our endpoints have to be both our max and our min. I know that my endpoints are the same height. And I know that now they're both my max and my min.
You're saying for that specific chart?
No, so now, if this is not the case, if my max and my min do not occur somewhere in the interior, then they have to be the endpoints.
Oh.
So I'm telling you some information about my function now. Here's the information I'm giving you about the function.
There's straight line.
Information 1, yeah, you jumped right to it. I tell you that the height at A and the height at B are the exact same. And I tell you that A and B are both the absolute max and the absolute min. What does a function have to be?
Straight.
A constant function.
Or a straight linear function.
Right?
Yep, that's
Right? Okay. So, if the max and min are at the endpoints, and f of A is equal to f of B, then f of x has to be some constant function.
And so all of them are 0?
And so, the derivative is 0 at any point you pick in between A and B.
Yep.
So either a max or a min occurs somewhere in the interior, in which case the derivative is 0 at that point, or the max and min are both at the endpoint, and now the derivative is 0 anywhere in the interior. So in either case, I can find a point in the interior such that the derivative is 0 there. Good?
Yes, sir.
Yep.
Okay, so before we move on to proving now the mean value theorem, let's do one quick example using the mean value theorem. So first up, we're going to prove that this function has only one solution. There's only one number x I can plug in here such that it's equal to 1.
Yep.
We're going to prove that. Now, where is this function equal to 1? That is when, subtract 1 from both sides, that happens when x cubed plus 3x is equal to 0.
Yeah.
You with me? Okay, so let's label this function f of x now. F of x I'm going to call x cubed plus 3x. Now first off, so where this is equal to 0, that same x makes this equal to 1.
Oh yeah, because they're connected anyway.
Right? Because where did I get this function? I just subtracted 1 from both sides. Okay, so wherever this function is equal to 0, that same x makes this statement up here true.
Yeah.
You see that? Okay, how do I know that there's an x that makes this statement true? In other words, how do I know that there's an x that makes this 0?
Because
There has to be a bigger amount.
You can just see plug in 0 definitely works.
Yeah.
You see that? Okay, now, how do I prove that 0 is the only solution there? There's no other x. I can make that true.
How do you prove that? That's a good question.
How do you prove that? That's a good point. All right, so now let's look at the derivative of this thing. What is f prime of x equal to?
3x to the power of 2 plus 3.
Now, what do you notice about the derivative?
You can't take 0.
It's a parabola.
It's a parabola. It's a parabola shifted up.
3 units.
How do I get a negative number out of there? Where is the derivative equal to 3? Where is the derivative equal to 0?
It's impossible.
Sorry, I meant where is it equal to negative 3? You can't get negative. Where is it equal to 0? Is the derivative ever 0?
No.
No.
No. What's the smallest the derivative can ever be? 3. So if this function had two solutions,
How could it be 3?
you plug in 0 and it spits out 3.
Oh.
And that's the smallest you could possibly make the derivative.
Yeah.
So we know that whatever this function looks like, it goes through 0 at 0, right?
Yeah.
And how do we know that in whatever it doesn't secretly come back down and go through 0 again somewhere later? How do we know that this is impossible?
Because
If this happened, then the derivative somewhere in between would have to be 0.
why?
That's what we just proved with Rolle's theorem. If your function at A is the same as your function at B, if your function has the same height at two places,
Yeah.
then the derivative has to be 0 somewhere in between. That's what this theorem says.
Yeah.
If f of A is equal to f of B, then there has to exist some c between them, such that the derivative at c is 0.
What if it's just a straight line above 0 mark?
What if it's what?
What if it's a straight line above the 0 marker?
Show me what you mean.
Just draw a straight line. Like literally just draw.
So our function has to go through 0, 0.
Oh, it has to?
Yeah, we found out that our function contains a point 0, 0. Now we're saying, how do I know my function doesn't secretly cross the x-axis again? How do I know it's secretly not 0 somewhere further down the road? We're saying that's
Because it
impossible.
can't get 0 because it can't get negative.
You see it now, because the derivative can never be 0.
Yeah.
Rolle's theorem says that if it got 0 again somewhere else, then the derivative would have to be 0 somewhere in between. But our derivative is always positive,
So you can't.
so it can't be 0 somewhere in between. And so, this function has only one solution. So this equation has only one solution. So we found the solution, and now we prove that that's the only solution. The only real solution.
Okay, but how does that theorem work? Because why can't I have a straight line just at like positive 3?
Okay, so you're saying, just do this.
Yeah.
So what does Rolle's theorem say? It says if your function has the same value at two different points, A and B, which it does, right here and right here, right?
Yep.
Then the derivative has to be 0 somewhere in between. Is there anywhere in between where the derivative is 0?
Entire thing.
The entire thing. That's one of the special cases that we handle.
Okay, I'm still processing.
Takes a couple times for it to sink in.
Yeah.
Alright, think you got it?
Yeah.
Exactly using it. Alright, so now let's prove the mean value theorem. So remember with Rolle's theorem, we proved that if the function has the same height at 2 points, then the derivative had to be 0 somewhere in between. We're going to be using that fact for the mean value theorem.
Okay.
So don't forget what we just covered. That's got it all. Let me put this quickly real quick. Okay. So the mean value theorem. Here's what we're proving. Draw a picture of it to the side. Here's some function f of x.
Okay.
Take some closed bounded interval of our function from a to b.
Yeah.
There it is. I am proving that there must exist some point between a and b in my domain such that the slope at that point is the same as the average slope between the points. So I'm looking for some point c such that the derivative at c is equal to the slope going directly from our start point to our end point.
Okay.
Okay? Now, we're going to be using this line in our proof. So I'm going to write out the equation of that line. Don't want you to get confused by this.
Okay.
What is the equation of this line?
It's gonna be.
So go back to our basic equation that we've used 1,000 times. Here's the equation of a line that goes through a point and has the slope m.
Okay.
You with me? We'll use this as a point that it goes through. We could have used this one, doesn't matter. We'll use this one.
Okay.
So what's our y1?
F
F of a. What's our x1?
A.
A. Okay, good. Now what is our slope? Our slope is going to be rise over run. Right? So what's our rise?
FB minus FA.
FB minus FA. Good.
And then a run.
Minus FA. And our run is what?
A minus B.
B minus A.
B minus A.
If you do the B first here, you have to do the B first here. You could have swapped both of them.
Oh, really?
And it would work.
Yeah.
Just make sure you do the same order. Okay, so the equation of our line is y minus y1 is equal to m times x minus x1. I'm just going to move the y1 to the other side. Here it is. And now let's plug in everything we know. What's our m? It's right here. So plugging in our m.
Okay.
X minus x1 was a plus y1.
Okay.
So g of x here is just the equation of that line. You with me? Okay, so here's exactly what we're going to prove. If x is continuous on the closed bounded interval a to b, and it's differentiable on the open interval a to b, so no corners,
Yeah.
then there exists some point c between a and b such that the derivative at c is equal to the slope of this line, which is f of b minus f of a over b minus a. The slope at this point is the slope of this line.
Okay.
You understand what we're proving? Picture makes sense?
Yeah. Okay. That makes sense.
Okay. So let f be continuous on the closed bounded interval a to b and differentiable on the open interval a to b. And we're going to let g of x be that line. This is that. Just writing it out.
Okay, gotcha.
Cool. Now I'm going to define some new function, h of x. H of x is going to be equal to f of x, whatever our f is. We don't know anything about our f, except for that it's continuous and differentiable. So h of x is going to be f of x minus g of x. So I'm doing f of x, our f, minus our g. Now why am I doing that? What is the height of f at a?
It's F of A.
And what's the height of g at a?
F of A.
F of a. Notice that both those functions have the same height here, and both those functions have the same height here. So when I do one function minus the other function, what's their height going to be at a?
0.
And what's their height going to be at b?
0.
So they're going to have the same height at a and b, and so I'm going to be guaranteed that this new function will have a derivative 0 somewhere in between using Rolle's theorem.
Okay.
So f was some random function. I chose g such that f minus g is going to be 0 at this point and at this point. So it's going to have the same height at this point and at this point. And so Rolle's theorem tells us it's going to have a derivative 0 somewhere in between.
Okay.
And then we'll use that to finish off our proof. With me? Okay. So there's h of x. Let's really quick find out what is h of a. So remember, h of x is just f of x minus g of x.
Okay.
So what is h of a going to be? What's the height going to be at a?
It's gonna be 0.
It's going to be 0. So let's do the algebra and see that it actually comes out 0. But our intuition's screaming 0, right? But let's actually plug it in. So when I plug in a, that's going to be f of a minus whatever I get for g when I plug in a.
Okay.
So I'll just write g of a here for a second, and then we'll rewrite it again. So it's going to be f of a minus, let's see, what do we get when we plug in a for g? So here's g, right? And I'm replacing my x with a.
You get the same thing. You get the same thing except for remove that.
Oh, you get f of a.
Well, just think through it carefully. So I'm replacing my x with an a. That's what it means to plug in a for g, right? It means replace your x with an a. So replace x here. This is my only x. Everything else is a constant. So replace x with a. What's a minus a?
Oh, yeah, f of a.
Okay, so yeah, we're calculating g of a. G of a.
Yeah, g of a.
So replace our x with an a here, and what do we get?
That's 0.
0. 0 times anything is
0. So
plus f of a is.
f of a.
So g of a is the same thing as f of a, which we already knew. The height of g at a is f of a. Right? So h of a, remember h is the difference between the two functions. It's the difference in their height. So h at a is f of a minus g of a, which it turns out is f of a minus f of a is 0. Now what is h of b equal to? Well, this is going to be equal to f of b
Minus g of b.
minus g of b. Let's plug in g of b. So that's going to be f of b minus f of a over b minus a, all times we're replacing our x with a b.
Yeah.
And then finally plus,
F of a.
oh wait, we're subtracting, so that's going to be minus. Because we were subtracting g of b. So f of b minus g of b. So I have to distribute the negative to both terms.
Oh.
I could have done minus like this, minus g of b. Maybe that helps better.
Where did you get the minus?
F of b
Okay.
minus g of b.
Oh, okay. Duh.
Just plugging in b to this.
Okay. Yeah, I see.
Okay. Now notice we have a b minus a in the denominator here, and a b minus a in the numerator. So that cancels out with that. You see it?
Yeah.
So we get f of b minus f of a plus f of a is just f of b.
Oh, duh. Yeah.
F of b minus f of a plus f of a is
F of b.
f of b. This says make it negative.
So negative f of b.
So we get f of b minus f of b is
0.
Whoa. Where did you get the other f of b?
so far we've got f of b. That's this term.
Okay.
Minus
Oh, okay.
everything we got in the brackets,
Which is just f of b.
which is just f of b, which is equal to
0.
0. Good. So h of a is 0. H of b is 0.
That means you'd be
So h is a continuous and differentiable function, and it has the same height at a that it does at b. So what do I know about h?
It's 0.
Its derivative is 0 at some point between a and b.
The whole thing.
No, not the whole thing.
Oh, yeah, you're right.
Remember, h is giving me the difference here. So h is 0 here, it's like 1 here, it's like 2 here, it's like 3 here, it's like 4 here, 3, 2, 1, back to 0. H is telling me the difference between these two things. The difference in their height.
Oh.
One minus the other.
Okay, that makes so much more sense.
Okay, that's what h is defined to be. It's the difference between the two functions.
Okay.
And since f is continuous and differentiable, and g is continuous and differentiable, then f of x minus g of x is continuous and differentiable, so h is continuous and differentiable.
Yeah.
Okay, so I know h is continuous and differentiable. I know that h has the same value at a that it does at b. And so using Rolle's theorem, the derivative of h has to be 0 somewhere.
Yes.
So then by Rolle's theorem, there must exist some c between a and b, such that the derivative of h at c is equal to 0. You with me?
Yeah, that makes sense.
Now what is a derivative of h? Let's look at it up here. H is equal to this. So what is a derivative of h? What is h prime of x? How do you take a derivative of the difference of two things? It's just the derivative of the first thing minus the derivative of the second thing. Right? If I asked you, what was the derivative of x to the 5 minus x to the 4? You know it's just the derivative of that minus the derivative of that.
Yeah.
It's just 5x to the 4 minus 4x cubed. Easy as pie, right?
Yep.
Same exact thinking here. So, I know that the derivative of h with respect to x is the derivative of f minus the derivative of g. And I also know that the derivative of h at the point c is 0. So plugging c into this
0.
gives us 0. Perfect. So f prime of c minus g prime of c has to be 0. Move g prime to the other side.
Okay.
And that gives me f prime of c equals g prime of c. Now, I should have made one more note before doing this proof, so put a pause in it right there for a second. What is a derivative of a line?
It's constant.
It's 0.
It's,
Well, it's line straight.
what is the derivative of this line?
It's
a constant, but what is it? What does the derivative give us?
the slope.
The slope.
So
What is the derivative of this line?
Range
Just slope.
The slope. What is the derivative of this equation?
The
Right? If y is equal to this, then what is y prime equal to? Just m, the slope.
Okay.
You can see that real easily. Let's see that real easily. Solve for y again really quick. Y is equal to, I'm going to move this to the other side, but let me multiply this out.
Okay.
So m times x minus m times x1, and then plus y1. You with me?
Yeah.
What's the derivative of a constant?
0.
0. A constant times a constant, take its derivative,
0.
0. What's the derivative of m times x with respect to x? What is the derivative of 5x?
5.
5. What's the derivative of mx?
M.
M.
Okay.
Okay. So the derivative then of g of x is what?
The slope of g.
Its slope, which is this thing. That's the slope of g of x, right?
Any line.
At any point on g, that's its slope,
Yeah, that's true.
right?
Yeah.
Okay. So I know that f prime of c minus g prime of c is 0,
Yes.
which gives me that f prime of c is equal to g prime of c.
That's correct.
And I know that what the derivative of g is anywhere, including at the point c. It's just a slope.
Slope.
So that gives me that since the derivative of g anywhere is just its slope, then that gives me that the derivative at f, the derivative of f at the point c is equal to the slope of g,
The same. Yeah.
which is what we were trying to prove.
Oh yeah.
I was trying to prove that the slope, that there is some point c such that the slope at c is the slope of our line connecting these 2 points.
Okay.
And that's what we proved.
Yep.
It's a pretty cool proof. Think you got it?
Yes.
Okay, let's do 2 smaller proofs. You can ignore that. That was if I didn't have time to write them out. Okay. So now looking up here, here's what we're going to prove. We're going to prove that if we have some secret function, I don't know what my function is, but the derivative of the function is 0 everywhere on its domain, then our function must be a constant function.
Okay, that makes sense.
It's basically like we're calculating our first integral now.
Yeah. The reverse. Oh.
Yeah, the reverse of a derivative. I'm looking for a function such that when you take its derivative, you get 0.
So
That's another way to say it. What's the function? So we're going to prove that this function is a function that makes that its derivative is always 0.
always.
Good? Okay. Now first off, since the derivative of the function is 0 everywhere, then the derivative exists everywhere, and if a function is differentiable, it's continuous. So I know that my function is differentiable and it's continuous. F is. Why? Because it has a derivative everywhere.
Yeah.
And we already proved that if a function has a derivative at a point, it's continuous at a point.
And then it's already differentiated.
Right. We already are guaranteed it has a derivative, so I know that my function is f must both be differentiable and continuous.
Okay.
With me?
Yes, sir.
Okay. So now, how am I going to prove that my function is continuous? Here's the way I want to prove it. I'm going to show that for any 2 points you pick out of the domain, pick any 2 points you want,
Okay.
the height of those 2 points is the same.
Yeah. That's by default, isn't it?
Well, you're thinking, well, since it's constant, that's going to be the case. Now reverse your thinking. I'm trying to prove it's constant. How am I going to show my function is constant? I'm going to show you that pick any 2 points out of the domain you want. Their height is always going to be the same, no matter which 2 points you pick.
Yeah.
Therefore, all points in the domain have the same height as each other. Right? If I told you that, I've got a room full of kids, and pick any 2 kids in the room you want, they're the same height, I'm guaranteed that everyone in the room is the same height. Make sense? Same thinking here. Pick any 2 points in the domain you want. I'm going to show you that they give you the same height. Therefore, the whole function across the domain has the same height. Therefore, it's a constant function.
Yeah.
That's the theme. Okay, so let x1 and x2 be any 2 points in f's domain.
Yeah.
We're going to let x1 be the smaller of the 2 numbers. So x1 is on the left, x2 is on the right.
Okay. I mean, this would better.
Right. It's like let x1, well, I won't say that. Bad analogy. But yeah, doesn't matter which one. If x2 happened to be the smaller one and x1 happened to be the bigger one, relabel them.
Yeah.
Okay. So now, it remains to show that the height at x1 is equal to the height at x2. That's what we're trying to show, and then we're done. Make sense?
To prove.
Huh?
Yeah, okay.
If I can show this. So if I can show this, then we're done. So that's what I need to show. Okay. What do I get from the mean value theorem? By the mean value theorem, what we just proved over here,
Yeah.
there has to be some point between x1 and x2
Yeah.
such that the slope at that point is equal to the slope of the line connecting x1 and x2. This is the slope of the line connecting the points x1, f of x1 to x2, f of x2.
And you're saying that there's some point on the...
So there's some point between x1 and x2 such that the slope at that point is equal to this slope.
Yeah, that makes sense.
Just the rise between the 2 points over the run between the 2 points.
Yeah.
Okay. So, I know that f of x2 minus f of x1 over x2 minus x1 then must be equal to what? I know that there's some point c such that the derivative at c is equal to f of x2 minus f of x1 over x2 minus x1.
0.
So, f of x2 minus f of x1 over x2 minus x1 has to be 0. How do I know that? Because my derivative is 0 everywhere.
Oh.
So f prime of c is 0.
Yeah.
Good. So I know that this is equal to 0. Multiply both sides by x2 minus x1.
You get 0.
And I get f of x2 minus f of x1 is equal to 0. Right? Move x1 to the other side, and what do I get?
F of x2 is equal to f of x1.
Therefore,
F of x.
yeah, so, which gives me that f of x2 is equal to f of x1. Or in other words, f of x has to be a constant function. I showed pick any 2 points you want, they have the same height. Therefore, our function is a constant function.
What does that box mean?
And thus it is demonstrated. That's what you put at the end of every proof. It's
So weird.
a mark to the reader to let them know the proof is now complete.
Have you been doing that all of this year?
Yes, most
I've
likely.
not noticed that. Anyway.
Anyway, next little proof. I am now going to prove that if 2 functions have the same slope everywhere, then they only differ from each other by a constant. What on earth does that mean pictorially? Let me draw two functions that have the same slope everywhere. Here's one. Now I'm going to draw another function that has the same slope everywhere. Here's the other one. Those two functions have the same slope everywhere, if I drew my picture good enough, right? And so the difference between this function and this function is just a constant. If this was a function, y equals x squared plus 3, then this must, well, we had it shifted to the left. Just to keep it simple, let's pretend that the y-axis came right down the middle.
Okay.
Terrible picture, but you know what I'm trying to say, right? Then this one down here might be something like y is equal to x squared minus 7, right? And so they only differ from each other. If I did this minus this, I would just get a constant. What's this minus this? It's 10. And so the difference in height between any 2 points on these functions is just 10. This function is this function, just shifted 10 units up. So if I have two functions, no matter what they look like, it doesn't matter what weird thing they look like now, if their slope is everywhere the same, then the difference between the two functions is just a constant.
Is that a proof?
That's what we're going to prove.
Okay.
So now read it here in symbols and hopefully it makes sense. If we have two functions f and g, such that the slope of f is always equal to the slope of g, then there must exist some constant such that f of x is equal to g of x plus a constant. I can add some constant to g of x and get f of x. If I add 10 to this, I get that.
Okay, that makes sense.
That's what we're proving. Good? Okay. So, I think I'll need some of that vertical space, or horizontal space, I keep saying that. Alright, so let's assume that, oh, are we there?
We have like
We have 3 minutes.
3 minutes.
Oh my goodness.
So you can prove
Alright.
this and then we can just not do the examples.
Let's prove that, so assume that these two functions have the same derivative everywhere. You with me?
Yeah.
And I'm going to let h be their difference. I'm trying to prove that h is a constant. If h is a constant, then f of x, well, we'll see it. So, what is h prime of x then?
It's
F prime of x minus g prime.
F prime of x minus g prime of x, right?
where did you get that from?
Just take the derivative.
Derivatives.
What's the derivative of h
Oh, I didn't see that. Okay.
f prime minus g prime? You with me?
Yeah.
But f prime of x is equal to g prime of x.
0.
So that's 0. So h prime of x, its derivative is always 0. And if a function's derivative is always 0, what's the function?
Constant.
A constant function. So h of x is equal to c.
Therefore,
Or in other words, that's the same thing as saying c is equal to f of x minus g of x. Move your g of x to the other side, and you get f of x equals g of x plus c.
cool.
Good? Alright, unfortunately, can't do our examples. Ran out of time. But that was all the new theory. So, you should still be good to do your homework. Sorry that we don't have time to do the examples.
We are supposed to do that 2:30, right?
We're supposed to be down there.
Alright, yeah, you guys are on.